technically, you're done with chapter 5, but this last video is kind of a bonus video for you to help you solve problems related to pressure in pipes and tubes. Now, the thing to note that is the recent past years have not had these kinds of questions, but just in case they come out, I just want to let you know, pull out some really old questions so you can have a look at it. So we have pipes like this, V shape, U shape, W shape also got, and we're going to look through 4 questions, exactly what you see on the screen. 4 questions to help us think about tubes. But first, a simulation. So anything you need to know about U-tubes and pressure tubes can be done in this GeoGebra simulation. So here is an example of a U-tube. Okay, let's say I set the density to be the same. 1000.1. How about that? Okay, the theory is this. If the density of the liquid is the same, then it should be evenly distributed across the tube. Makes sense, okay? So what is this P gauge thing here? Let's play around with it. Let's make the density of this liquid more. So if I drag this, more dense, it actually affects the liquid on the other side. Okay, see what's happening there? Ooh. So now this side's liquid is more dense and it's kind of like filling up this whole bottom part. And you have a difference in height. So from here to here is the more dense liquid, from here to here is the less dense liquid. So the pressure gauge at point A, at this point, there's going to be this much 760 pressure pressing at this point. Now at the bottom here is all the same liquid, so usually we can just choose a point where the liquid is different. So on the right side, here, the pressure here is going to be all this liquid on top pressing on there. And notice, it is 760.75. Wait, that's exactly the same as the left side. That means, at this point, this whole tube thing is in equilibrium because the pressure at this point is the same as the pressure at this point. So they are balanced. The liquid won't move anymore. Now, if the liquid on the left side is less dense, so kind of illustrate, this lighter color is where the lighter liquid is. Okay, so maybe something like this. So at the same point, if I want the same pressure, I would need more of the less dense liquid to press down at this point. And this one more dense, right? So I need lesser height to press down to get the same pressure. So see 373, 373. So that's the whole idea of pressure in tubes. It's all about left side balance, the right side. Pressure must be the same at this same point. So if I add an extra mass, what is a mass? This little gray thing here. Maybe it's like a block or something like that. Add extra mass. Oh, then now this left side got help to press down the liquid. Means the pressure from this mass and the pressure from this height of water equals to the pressure of this entire column of different liquid. So see, pressure on the right at this point is 1110, left side 1110. So that's the whole idea. Left side equals right side, and you should be able to solve all kinds of questions based on that. First on the list is the V-tube. The V-tube here, one side is closed and the other side is open. So remember I talked about in the simulation, the left side must equal to right side. The liquid's not moving, means the pressure on the left part of the tube equals to the pressure on the right part. But what does that mean exactly? Let's clarify a bit. So at this level, this is where different things happen, because suddenly there's gas and the other side there's extra height of water. Means at this point, the pressure here, because of that gas, should be the same as the pressure on the other side because of the gas and the air and everything else. So how I can write it out is pressure on the left should be equal to the pressure on the right at that level, that dotted line level. Because, well, if you want to consider the whole thing all the way to the bottom, here the pressure will definitely be the same because it's same water, same height some more. So we want to care what's different. So what's different is above this line, different things happen. Pressure on the left. Did they tell us what's the pressure of the gas? No, they're trying to find that. Okay, so we're trying to find what is this P? Okay, so on the left side, I have the pressure of the gas. I don't know what that is. I'll just say P gas. Anything else on the left? It's a closed tube, so it's just isolated. It's just pressure of the gas, nothing else there. On the right side, we have pressure at this point from this whole column of water vertically. So you need to remember hydrostatic pressure. P is rho GH. Okay, so you must write that down. The density of water times G times that height, which is 5 meters. Okay, any other pressure to add? Don't forget. This N is an open tube, which means there is also the entire atmospheric pressure pressing down on it. And they give it to us too. See here, atmospheric pressure. Okay, so open tubes, we need to take that into consideration as well, because you know the air has some pressure pressing down. So we need to add what other pressure is there? Atmospheric pressure. So I'll just write here PATM. So if we plug in all the values, density of water 1000, G 9.815 plus the whole atmospheric pressure. So what am I writing? 1.0. 1 times 10 to the 5 Pascal. Okay. Add all together. So 1000 times 9.81 times 5 plus 1 times 10 to the 5. You should get about 149,050 pascals. The unit of this pressure is Pascal. So if we run out to the answer, it's all 2 SF, so it'll be 1.5 times 10 to the 10 to the 5 Pascal. So this one is the answer for this V tube. The next one is called the U tube. This one is a bit funny. I want you to try it out. It's on page 28 if you have the handout. You can pause the video and try it out and come back and check, since you have like a basic understanding of how it works. This one don't have values. So remember, whenever there are questions that don't have values, means they want you to solve algebraically, using ratios, using equations, play around with the equations. Same thing that's happening here. Okay, the liquids are in equilibrium in an open tube, means they're just balanced, they're not moving up and down. What is the ratio of density P over density Q? Okay, don't worry about how you're going to find the ratio. Just stick to the basics, balance the left and the right. So, pressure in equilibrium, the pressure on the left side should be the pressure on the right side of this tube. So on the left side, what do we have? We have this very light colored, light colored liquid there. So there will be rho of that liquid P times G times the height, which is 2 of X. That's the height of that light liquid lah. Plus, okay, here I'm going to show you why we can ignore the bottom part. So let's say we want to plus this bottom part also. Okay, so that will be the O liquid Q. So density of Q, G times X. That's if you want to consider that bottom part. On the right side, what do we have? We only have Q. I forgot to mention. You see how this is open air? The tube is open, right? Means actually got atmospheric pressure also. Here also got, the other side also got. But you will see that they actually cancel out because both are open. Okay lah, let's write it down. Atmospheric on this side. So the other side will be the same liquid there. Okay, actually 2 of it. So you have liquid Q times G times the height. Total height will be 2x plus atmospheric pressure. So if you rearrange this a bit, atmospheric pressure minus atmospheric pressure. So these two fellas are out already lah. And actually, this one P, we can rewrite it as 2 rho PGX PQ, you can move to the other side actually. So, we'll move to the other side, -1, it'll just be rho Q G X. Where the 2 go? Nah, because here got 2, here got 1. So I move to the other side, only left 1 now, 2 minus 1 is 1. So this simplified equation, actually you can shortcut, you can jump here very fast. How? You just look at the pressure at this rate level. At this rate level, both sides got atmosphere, so the effect cancel out. So you just look at this column, which is 2 rho gx, and the other side, what's different is just this column here. So that will be rho q gx. So sometimes it's okay if you just shortcut and just write this one. But you need to choose the line where below it everything's the same. Okay? From here, how do we simplify? Oh, g and x can cancel out. Divide both sides by gx. So gx is gone. All that's left is 2 rho p equals to rho q. And they ask us, what's the ratio of density P over density Q? Okay, so we need to do density P over density Q, which means the ratio is 1/2. That's how you can find the ratio. So if you see tubes, don't just stand there and like, how to find density? What? Just write out all the pressures. Pressure on the left equals to pressure on the right side of the tube. Let's look at something a little bit more tricky. Question is like a YouTube, but it starts off slim, then suddenly become fat and come up. So this is on page 29 if you had a handout and want to try it out as well. 29, yes. Or just look at this one, take a piece of paper and try it out. Pause the video, come back and go through it together. So the basic idea is here, what is the height of the mercury column on the right side? And got all kinds of stuff pressing down. So the main idea is still the same. The pressure on the left side, total pressure, I should add, equals the total pressure on the right side. Means all this left side, oh, it's open air, so got atmospheric pressure pressing down also. The atmospheric pressure, the piston with some weight also pressing down. And then on the other side, closed tube. Closed means no atmospheric pressure pushing down on it. So just the air and the column H of water. So like previously, this thing is in equilibrium. The water's not flying around. So you can choose this level to be your reference, because below that is all the same. Mercury pressure is the same. So it cancels out. So what's different is above this line that I just drew. Let's list out all the pressure on the left and on the right side of the U-tube. Okay, I draw a divider. So on the left side, firstly, we have atmospheric pressure, PATM, plus the piston have some mass, so the heavy thing is pushing down. Weight is a force. How to connect force to pressure again? Think back. Pressure is force over area. So this heavy piston here, it's going to exert some force on that area. Did they give us a cross-section area in the question? Oh yes, they did. It's for a reason. Cross-section area, 5 times 10 to the power of -4 meters squared. Okay, so we do know that. So we can use that to find the pressure exerted by that piston. By the way, the pressure here we can simplify, change it to be just mg over a. Mg is the mass of the piston times the gravitational acceleration constant. So PATM plus mg over a, this is from the piston, that block. Need to plus anything else? No need lah. You can plus this mercury down here, but it's going to cancel out with the other side anyway. So no need lah. On the right side, what do we have? We have the trapped air bubble on top. You know what? I'm just going to call it P air. That's this one up here. P air, 5 times 10 to the 4. Plus the column of mercury pressing down. So that will be rho of mercury. What's mercury? Hg. Times gravitational constant times the height h. So there, I have my equilibrium equation for this U tube. The only difference why the area is different is when I'm trying to find the pressure because of the piston. Otherwise, the cross-section area doesn't really affect. So let's see, atmospheric pressure, let's plug in everything we know. It's given to us, is it? Yes, atmospheric pressure is 1.01 times 10 to the 5. Mg, 5 times 9.81 over cross-section area is 5 times 10 to the negative 4 equals to pressure of air that's trapped up there is 5 times 10 to the 4 plus density of mercury. Is it given to us? Yes. 13600 times 9.81 times, not enough space, h. Just nice. So plug in all the values to get h, rearrange everything, and let's see. I got roughly about I wrote it down somewhere, 1.1176 meters. The answers, if you check the thing, is in cm. So if I round it off a little bit, 2, so it'll be like 112 cm. If it's a two significant figure, 2SF, it'll just be 110 cm. This is for 2SF. So, YouTube, same idea. Pressure left equals to pressure right. And you just, from there, you just see what they want you to find. Now, the next one, a little bit more challenging. Okay, these are the rare ones. Out of all the past year paper, maybe it appear like once in many years. And then another one come out many years. But they're both in the same series lah. So this one is the W tube. Don't panic if you see like, W tube. This is on page 27, I think. Let me check for you. So check out this one. Here's a hint before I let you try it out. The W tube is essentially two U tubes joined together. So one U tube, another U tube. They just happen to be joined at one part. So try and use your YouTube skills, not the YouTube video, this YouTube pressure skills, and break down this W tube to see what you can do about it. And then come back, play the video, and we'll check how to solve it. So the question asks, what pair of values of H1, H2 is possible? The height. Conveniently, they gave us the values. We just need to know which one to choose. So don't panic when you see this. Just remember the basics. Pressure on the left equals pressure on the right. So for the first U tube, we break down the W into a U. Let's see. So for this one, this part. Okay, part 1 there. Pressure on the left side. Oh, by the way, I should say, I'm going to choose this level because this is where things are different. Here, left side is air, right side is water, or what? Mercury, sorry, not water. So the pressure on the left side is just because of this air pressure, air pressure there. So pressure on the left will just be 16000 with reference to this dotted line. Pressure on the right will be from this column of mercury here. So density of mercury times G times H1 plus there's the pressure in this part of the tube. I don't know why is it there, so I just put P lah for now. P. Okay. So that's for the left side. How about the right side? I'm going to write on the right side. So the right side, you can kind of break it down into another U tube. Here on the left side, I'm going to choose this red, not this red, this blue dotted line as my reference point, because below that, everything's the same. Above that, that's when the pressure difference starts. So what's pressing down on this second U tube? First, there's the pressure P in the middle, so this one here. Then there's a column of mercury. So rho G H2 equals to, what's on the right side? Air pressure of 8,000 Pascal. That's it. Okay, now what? Now I have two equations. and I somehow need to relate H1 and H2. What if we sub the P and P together? So I equate, somehow I can sub in or equate these two P's. Sounds like a plan. So I'm gonna rearrange and equate, sub or equate, depending on how you want to phrase your maths. Sub and equate equation 1 and 2. So it's sub equate the P's, because that's the thing that links these two equations, or link these two U tubes together. It's the pressure in the middle that connects them. So on one side, I will have 16000 minus rho GH1 equals to P, but the P equals to the other side, which is 8000 minus rho GH2. This, I skip a step, I rearrange, so solve for P, then I equate both of them. So now I can do some fun stuff already. What can I do now? Let's try to rearrange everything and make it cleaner a bit. How about that? Okay, so let's move down here. So 16,000 minus 8,000 equals to rho GH1 minus rho GH2. So then I will get 8,000 equals to rho G H1 minus H2. Oh, wait, I can do one more thing. If I know rho and G so I can divide it out. So 8,000 divided by rho G. What's the rho of Mercury? 13600 times 9.81. Okay, so that's, wow, that's very, very small. Let's change it to cm. Okay, so I should get roughly 6 cm on the left side, and that 6 cm equals to H1 minus H2. So now all we need to do is go through all the choices to see what are the possible heights for this W tube. H1 minus H2 is 6. So let's look at A. A confirmed out already. B also out. C, that is H2 minus H1. Wrong. It's supposed to be H1 minus H2. So the answer in this case is D, the best choice, because H1 minus H2 is 6. So same thing here. If you ever feel like stuck, not sure how to do it, just do your good old pressure on the left equals pressure on the right. If it's a W tube, means there's two U tubes joined together. So this is still pressure on the left equals to pressure on the right, but for the second U tube. Same thing. The final example is coming up next. This one, I can consider it kind of like a sort of a challenge question. I guess it's the hardest among all the tubes, but it appeared like once in a very long while. So this one is a W tube also, but they're asking for different things. This one, if you're feeling adventurous, you can pause it and try to solve it. This is on, what page is this? Next page, 28. So this is page 28. If you want to try it out and be adventurous, please feel free to do so. Okay, so this W-shaped tube has 2 bits of mercury stuck inside there, like before. This is an interesting sentence. Atmospheric pressure is equal to the pressure that would be exerted by a column of mercury of height 7600. So what that means is, let me just sketch it very quick for you. If you have a pipe of mercury that is 760 mm high, the pressure at the bottom is atmospheric pressure. So this is atmospheric pressure. That's how people in the old days measure atmospheric pressure. Okay, so if you have a column 7600, that's what it means, atmospheric pressure. A side note is, last time people, they have so many units for pressure. They say the atmospheric pressure is 760 mmHg. This used to be a unit for atmospheric pressure. mmHg just means millimeter of mercury. So this is a mercury column. Hg is the, you look at the periodic table, mercury is Hg. So used to be mmHg, now we use Pascal, Newton meter, and so on and so forth. Okay, let me rub this off so we have some space for this madness. Okay, remember I say don't panic if you see W tube, just break it down. Okay, so here are our choices, but we'll look at that later. Okay, whew, let's break down this W tube, cut it in half and treat it like two separate U tubes. So on the left side, what do we have? Atmospheric pressure. Okay, good to know. You can say, will atmospheric pressure cancel out? No, because your U tube now, it's on the right side is air pressure stuck here, is not atmospheric pressure like before. So if it's just an actual U tube, both side atmospheric pressure, then you can ignore that. But this one we cannot. So okay, never mind. On the left side, we have atmospheric pressure. Where are we going to choose our reference line? Here, let's choose this. Because below this is all mercury, all the same pressure, so nothing interesting. Everything above this, oh, then there's different stuff happening, so we want to be careful about that. So atmospheric pressure on the left. Then you have a mini little column of mercury here. So rho Gx equals to, what's on the right side? Air pressure at P. We don't know. Let's just call it P. Sure. P. So that's for the first U tube. The other side, we have, let's see. We're going to choose, I will choose this as the reference line. Because below that, it's all just mercury. Same pressure on either side. So they cancel out. So on the left side, first we have pressure P equals to, what's on the right? What's above the red line on the right side? We have this mini column of mercury. So that will be rho G. Oh, we don't know the height. Hey, wait. We know 50 millimeter minus Y. Just remember this is in millimeter, okay? Wow, that Y is ugly. Let me rewrite it. Y. Anything else on the right side? Pressing down on this red line. Atmospheric pressure, don't forget. So PATM. I think that's it. Okay, so this is very similar to the one before. We have a bunch of stuff we don't know, but we know how these two U tubes are connected, and that is through this pressure in between both wings of the W. So we can equate both. This one equate with this one. So right here, equate. So what we get then is atmospheric pressure plus rho Gx equals to rho G 50 in mm minus Y plus PATM. Oh, look at that. The PATM, if you move this left side one to the right, then they cancel out already. Okay, good. So eventually, they do cancel out, but at the beginning, they don't. So now what do we have left? Rho Gx equals to rho G50 minus Y. So I say rho Gx equals to rho G50 minus Y. Rho and G, same mercury everywhere, right? So consider, you can divide both sides by rho G and it's gone. So all that's left is X plus Y equals to 50 mm. So now you have to go through and check your answer. X plus Y should equal to 50. You look at A, nope. B, possible. C, possible. D, nope. The last one is where we kind of have to think carefully about mercury and atmospheric pressure. They are asking us what is P inside that middle section. Could we calculate it? I think we can. So here, let's go back to equation 1. So this is equation 1, equation 2. Let's go back to equation 1. Let me draw a line first. I need to find what P is. I need to sub in some kind of values. So, equation 1, P, we're trying to look for is atmospheric pressure plus rho Gx. Do we know the atmospheric pressure? Think about it. Do we know the atmospheric pressure? Actually, we do. The tip is right here. Atmospheric pressure is basically 760 millimeter of mercury pressing down on you. Psh, that is atmospheric pressure. And the other thing to note, go back to the question, look at that. It says after that, the pressure P is expressed in this way. So pressure P is not in pascals, it's not in newtons per meter, it's actually in mmHg. Remember that weird unit I mentioned at the start? So, firstly, atmospheric pressure, PATM, you can express it as 760 mmHg. That is the value of atmospheric pressure. Okay, it's just 760 millimeters of mercury pressing on you. Plus rho gx. Rho gx means this small thing here. So how many millimeters of mercury is that? We don't know. We have to try it out. Okay. So maybe let's say I choose answer B and try it out. I say it's 20 millimeter of mercury. That's literally the unit of pressure, the old school way, 20 mmHg. So that means if my X is 20, my pressure P should be 780 millimeter of mercury. And that is correct. So it is the answer. But what about C? Let's try it out. If you do 760 plus 30, you should get 790. Oh, but it's 810. So this 810 here is wrong already. So in that sense, B is correct. Now, if you're confused, like, oh, what just happened? The only new thing that happened here is the mmHg stuff. This stuff. Okay? It's just saying it's another way of expressing pressure in terms of how many millimeters of mercury is stacked on top of you. That's the pressure. Okay? So that's all for this YouTube series, this add-on for you to help think about pressure in tubes better. So I hope you had a adventurous, long season of learning Chapter 5, because we've gone through all of this. Make sure as you revise the last bits that you are familiar with density, pressure in fluids, and upthrust force. You need to be able to explain that. So that's all for Chapter 5, formally finished.